Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our class 12th physics playlist we will study the force on moving charge when placed in uniform magnetic field. We will learn how the direction of force is obtained by Maxwell right-hand corkscrew rule, or more convenient Fleming's left-hand rule. We'll do some exam-centric numerical problems. So let's start study of force on moving charge in magnetic field. A charge q moving with v velocity in magnetic field of b Tesla experience a force given as q v cross b, and if angle between velocity of charged particle and surrounding magnetic field is theta, then this cross product of v vector and b vector becomes vb sin theta and force become qvb sin theta, and the direction of vector force as a result of cross product of velocity vector and magnetic field vector is given by Maxwell right-hand corkscrew rule. The direction of resultant force vector is perpendicular to the common plane of velocity vector and magnetic field vector, and force is normal to VB plane, and its direction is given by Maxwell right-hand corkscrew rule. When screw axis is oriented in a cork perpendicular to VB plane, and from right hand screw is rotated from first velocity vector to second magnetic field vector through small angle by right hand, then the progress of screw in cork here in upward direction perpendicular to this VB plane indicate the direction of magnetic force on moving charge. The direction of resultant force vector as cross product of two velocity vector and magnetic field vector can also be obtained by right hand thumb rule, and thumb placed perpendicular to VB plane indicate the direction of resultant force when the finger of right hand are curled from first vector to second vector through smaller angle. So this thumb indicate the resultant force direction from cross product of velocity vector and magnetic field vector as shown in this figure. The direction of force on a moving charge in magnetic field can also be obtained by a more convenient manner by Fleming left-hand rule, and we'll learn and apply Fleming left-hand rule in our subsequent examples. Force on moving charge in magnetic field is given by this expression, and cross product of velocity vector and magnetic field flux density vector is written as Vb sin theta, where V is velocity of moving charge, B is flux density of magnetic field, and theta is angle between V vector and B vector, and the force become Qvb sin theta. Now in these four conditions, the study of force is important from examination point of view. If velocity is 0, that means charge is stationary and placed in magnetic field, it won't have any force. So magnetic field will not exert any force on stationary charge, whereas electric field produce force on both stationary as well as moving charge, whereas magnetic field can produce force only on moving charge and it won't produce any force on stationary charge. Now if particle is charge wise neutral, won't have any charge, then magnetic field will not exert any force on uncharged particle. So a moving neutron or gamma radiation won't experience force in magnetic field as they are uncharged. Now one important point is that if angle between velocity vector and magnetic field vector is 0 degree or 180 degree, that means both velocity and magnetic field direction are aligned, then in that case sin theta becomes 0 and there won't be any force on a charge moving along or opposite to the field direction. And whereas for theta equal to 90, sin theta become 1 maximum and force magnitude will become maximum QVB. This example will explain the significance of angle theta between velocity of moving charge and existing magnetic field in force calculation, and it is given that an electron is moving with a velocity v at a distance d from a straight conductor in anti-parallel direction of current direction in conductor or in opposite direction of current flow will have a force F on it. We have to find out the amount of force on same electron moving with the same velocity, but the velocity direction is now perpendicular to the conductor. The separation of electron movement from conductor is the same d. So we know a current carrying conductor produce magnetic field in the form of concentric circle around it, and magnetic field direction is tangential to this circle periphery. In first case, when electron is moving in this one directed direction, we presume that positive charge is moving in just opposite opposite direction, and direction of velocity of positive charge and magnetic field got an angle 90 degree. Sin 90 means the force will become maximum QVB, and if we use right hand corkscrew rule or Fleming left hand rule, we'll found that this force is attraction in nature. So this electron will attract towards this straight conductor by F amount of force, and in second case, at d distance from this conductor perpendicular to current direction, the direction of magnetic field and velocity got 180 degree angle, and sin 180 becomes 0. So this electron movement won't have any force. So electron moving parallel to conductor current will have magnetic force, and electron movement perpendicular to conductor won't have any magnetic force. Force on a moving charge in magnetic field is given as Q times vector product or cross product of velocity vector and magnetic field flux density vector, and as per law of vector product, the direction of this resultant vector must be perpendicular to the plane which contain velocity vector and magnetic field flux density vector, as this yellow highlighted screen plane. First, identify the common plane of velocity vector and magnetic field vector and place a cork and screw axis perpendicular to this plane. Now, as per right hand corkscrew rule, for a positive charge, the direction of this resultant force given by cross product of velocity vector and magnetic field vector is obtained by movement of screw when it is rotated from first vector to second vector through smaller angle in this anti-clockwise direction, and for that movement screw will move out of cork. So our direction of force would be perpendicular to VB plane outward, as denoted by this dot symbol here. The direction of magnetic force on moving charge given by vector or cross product of velocity vector and magnetic field flux density vector can also be obtained by right hand thumb rule. And according to right hand thumb rule, the thumb of right hand is placed perpendicular to plane of velocity vector and magnetic field vector, and if curl of finger matches with rotation from velocity vector to magnetic field vector through smaller angle, then thumb will indicate the direction of force as shown here. So this logic, direction of force is normal to the plane of velocity and magnetic field, is very important. The direction of magnetic force on moving charge can also be obtained by Fleming's left hand rule, and this law is also more convenient than corkscrew rule. In Fleming left hand rule, we have to stretch thumb, forefinger and middle finger mutually perpendicular as shown in this diagram, and this forefinger is aligned along the direction of magnetic field, and then left hand is twisted by wrist, elbow or shoulder such that the central finger get aligned with direction of motion of positive charge, and if in case of negative charge motion, we have to align this finger opposite to the direction of negative charge movement, and in that case the thumb will indicate the direction of force on moving charge in this magnetic field. Now one can remember this assignment of force, magnetic field and velocity to thumb, forefinger and middle finger by a abbreviation father, mother, child, FMC, where F become force, M become magnetic field and C is current or velocity of positive charge. So it is F, M, C, force, magnetic field and motion of positive charge. Now during use of this Fleming's left hand rule, we must align first the forefinger along given magnetic field or assumed direction of magnetic field if magnetic field is not known to us, and then through wrist, elbow or shoulder, hand can be twisted to aligned thumb if direction of force is given, or we should align the central finger along the direction of velocity of positive charge motion, and when forefinger along magnetic field and one out of thumb or central finger is aligned with respectively known force or known velocity of positive charge, the remaining position of central finger or thumb will tell us the direction of unknown velocity of positive charge or force on positive charge, as the case may be. For clarity of concept and sound preparations, we'll practice all probable competitive exam patterns. In this example, three particles A, B dash and C are moving in a uniform normal upward direction magnetic field as denoted by dot in this yellow highlighted area. Now according to the travel path of A, B and C, we have to find out the polarity of these three particles. Now here this B dash moving particle goes straight undeflected. It means magnetic field won't exert any force on this, and here the velocity of B particle and magnetic field got a angle 90 degree, and in such conditions in magnetic field a particle moving with 90 degree won't have force, means this particle won't have any charge. So this particle is a neutral particle, and practical example could be neutron or gamma radiations. Now particle A have a anti-clockwise curvature and particle C got a clockwise curvature in this uniform normal magnetic field, and we can check the polarity of particle A and particle C by Fleming left hand rule. And when thumb, forefinger and middle finger are stretched mutually perpendicular, and this forefinger indicate the direction of normal upward directed magnetic field, and this middle finger indicate the direction of motion of positive charge, then the thumb indicate the direction of force on this C particle. That means this C particle is positive particle, and for A particle the direction of force is opposite to this thumb direction obtained for positive direction motion of particle. So this A must be a negatively charged particle, and it would have a force opposite to the direction of this positive direction force. So this particle C is positively charged and particle A is negatively charged. A particle of mass m and positive charge q is moving straight in horizontal line with velocity v in the combined effect of gravitation field and magnetic field. The linear velocity of particle is also normal to uniform horizontal magnetic field, and we have to find out the direction of magnetic field, whether is upward towards us or downward inside this screen plane, and the magnitude of magnetic field such that particle go undeflected straight. Now if particle is going straight undeflected with constant uniform velocity, it means acceleration or force on that particle is zero, or that means the two force of gravitational field acting vertical downward and magnetic force acting vertically upward are equal and opposite to produce resultant force on this moving particle zero. Now to produce upward magnetic force, if thumb, forefinger and middle finger are stretched mutually perpendicular to each other as shown here, and thumb indicate the vertical upward direction of magnetic force QVB for 90 degree angle between velocity vector and magnetic field, and this middle finger indicate the direction of motion of positive charge, then this forefinger indicate the direction of magnetic field normal to this plane upward towards us, and for magnetic relation gravitational force mg equal to magnetic force qvb, and this results in magnitude of magnetic field flux density as mg upon qv, where m is mass of particle, g is acceleration due to gravity, q is charge of particle, and v is linear constant velocity of particle. Two permanent magnet north and south produce a uniform horizontal magnetic field of B Tesla, and three moving particle have velocity. Particle A is inward to this plane perpendicular to the direction of magnetic field. Particle B have again velocity perpendicular to magnetic field but upward towards us, and C particle is moving in the same direction as that of magnetic field as shown here. Now force on C particle is 0 and force on A particle and B particle is in this blue arrow direction. We have to determine polarity of all three A, B and C particle. As for Fleming left hand rule, when thumb of left hand, forefinger and middle finger are stretched mutually perpendicular as shown here, and the forefinger is directed along the direction of magnetic field from north pole to south pole, and through wrist, elbow or shoulder the left hand is twisted such that thumb will come in the direction of given force, and when force direction and thumb get matched, this middle finger will indicate direction of motion of positive charge, which is perpendicular to this plane upward towards us as indicated by motion of B particle. So this B particle is a positive particle, and for a negatively charged particle, if this is a direction of positive charge movement, this cross will become motion of negatively charged particle for same direction of force. So this A is a negatively charged particle, B is positively charged particle, and both produce the same direction of force in this magnetic field. Now the force on this C particle is 0, but the reason for that 0 force is alignment of velocity vector and magnetic field vector, and when two got 0 angle with each other, sin theta becomes 0, and whatsoever the polarity of this C particle, whether it is positive, negative or neutral, it won't have any force. So the charge polarity of this C particle is uncertain and it is not necessarily neutral. It may be positive or negative too. We can also find out the direction of resultant vector of vector product of two vectors by mathematical concept of unit vectors. In our three-dimensional rectangle coordinate system, three perpendicular directions are known as x, y and z direction, and in mathematical notation, vector of one unit magnitude in plus x direction is represented by I cap. Similarly, in plus y direction, unit vector is j cap, and in positive z direction it is k cap. Now in vector product of unit vectors, if cross product of two identical vector I cap, z cap or k cap is done, then this product is always equal to 0, as angle between two identical unit vectors of same direction is 0 degree, and in cross product the resultant is magnitude of first vector, magnitude of second vector and sine of the angle between the two vectors, and for theta 0, sin theta becomes 0 and the magnitude of cross product becomes 0. So for all cross products of similar unit vectors, result is 0, and when two unit vectors are mutually perpendicular as I and z or z and k or k and I, then theta become 90 degree and sin theta become maximum equal to 1, and the magnitude of this cross product is 1 unit and its direction is perpendicular to the plane of I and j, and this z direction is perpendicular to xy plane, and when we rotate right hand screw in a cork from first unit vector I to z direction, the progress of screw in cork represent plus k direction for this vector product. Similarly, cross product of j cap and k cap become I cap and k cap and I cap become j cap. We can remember this by a simple notation. The cross product of two unit vector is a mutual perpendicular unit vector, and this direction concept is easy and convenient in use and can be remembered. The resultant unit vector from cross product of I cap and j cap or j cap and I cap is perpendicular to this xy plane, and it is either in plus k direction or minus k direction, and that depend upon order of unit vector and can be obtained by right hand corkscrew rule. And if we place axis of cork and screw perpendicular to this xy plane along z direction and rotate screw from right hand from I to j, then it will move in plus k direction, and if same screw is rotated from j to I, from first vector to second vector, it go inward in minus k direction. So this can be easily tested from right hand corkscrew rule. Similarly, for cross product of j cap and k cap, when right hand screw is rotated from unit vector j to k vector with axis perpendicular to yz along x axis, it will move in plus x direction, or results is plus I cap. Now this cross product direction of unit vector can be easily remembered if we place unit vector I cap, j cap, k cap in a clockwise cyclic manner. Then the cross product of two vector I and j is the third vector k cap. Similarly, cross product of j and k is the third vector I cap, and cross product of k cap and I cap is third vector j cap in clockwise cyclic order. And if this order is reversed, then the cross product of two vector I cap and k cap become, for this anti-cyclic rotation, the third perpendicular unit vector j cap but with negative sign. Similarly, j cap I cap become minus k cap and k cap j cap become minus I cap. This numerical example will enhance our confidence level. It is given that in an uniform magnetic field of 3 Tesla in I cap direction and 2.5 Tesla in j cap direction, an alpha particle having positive 2 electronic charge moves with 4 into 10 power 4 meter per second velocity in plus I cap direction. What is magnetic force in this moving alpha particle? Now we know force on a moving charge is given by q times cross product of velocity vector and magnetic field flux density vector. In place of particle charge. Alpha got 2 electronic charge, and electronic charge is 1.6 into 10 power minus 19 coulomb. Now the velocity is 4 into 10 power 4 meter per second in I cap direction, and magnetic field is 3 in I cap direction and 2.5 Tesla in J cap direction. And for product, 2 multiplied by 1.6 become 3.2. Now this 4 into 10 power 4 also brought in multiplication with this 10 power minus 19, and this I will be cross product with magnetic field vector 3 I cap 2.5 J cap. Now 3.2 multiplied by 4 become 12.8, and 10 power minus 19 and 10 power plus 4 become 10 power minus 15. And this product I cross product 3I become 3 times I cap cross I cap, and this become 2.5 times I cross J cap. Now I cap and I cap got the same direction. Angle between the two unit vector is 0 degree, sine 0 is 0. So this cross product becomes 0. And for cross product of two unit vector I and j in cyclic order is plus k, and 2.5 multiplied by 12.8 become 32, and our force become 32 into 10 power minus 15 in MKS Newton unit in plus k direction. We hope this informative learning video has taught the basic concept of force on moving charge in magnetic field, and now you can calculate the magnitude of force as well as find out direction of force by either corkscrew rule or Fleming's left hand rule. Our other learning video are equally useful in exam preparation and concept building. You can use them in your study and share them with your friends. And if you need our study notes and exam-centric online doubt clearing classes, do join the membership of our Sridevi Classes YouTube channel by clicking join button just beneath. Happy learning. Have a nice time. Thank you very much.